Okay, so hello and welcome back all students to another video tutorial about the supercoiled form of the DNA. In yesterday's lecture, we have already talked about how the supercoiling influences the structure of the DNA. In today's lecture, we would be just having a short recap for 5 minutes, and then we will be moving forward towards the activity of certain class of enzyme called as topoisomerases that will alter the conformation of the DNA in such a manner that they will alter the linking number, twist, as well as the Frit component in the structure of the DNA molecule. Now, how these different components are being influenced, which are these different components, and how their conformation is being altered in the presence of different enzymes. So in my last lecture, I have already told you about the supercoiling form of the DNA, that the DNA can be relaxed, can be negatively supercoiled, can be positively supercoiled. Certain students were asking about the numerical part. See, numerical part could be done by a book that is referred to as MCQ. I would be sharing that book also with you, as well as through CSIR in which numericals are being given. For example, there is, let us understand the concept with a numerical which is given here in the case of Pathfinder that you can observe. See, here in the Pathfinder, what is being given? In this question, it is being told that there is a BDNA, there is a linear BDNA consisting of 5,200 base pairs in length. Okay, so if there is a BDNA that has 5,200 base pair in length, then what would be the normal linking number of this BDNA? In the case of relaxed form, that is referred to as LK0, the standard linking number. The standard linking number can be tabulated by dividing 5200 divided by 10.4 number of base pair per turn, because each helix has 10.4 number of base pair per turn present within itself. You can look at the video part in which I would be visible to you all. Okay. So here I am visible to you all. You can look at me. Now see, I have brought a DNA for you, and this is the DNA that we would be talking about. Now see, if this DNA has 5,200 base pair present within itself, in its structure, in a particular helix, and in each helix there are 10.4 number of base pair per helix, then what would be the standard linking number? The standard linking number can be tabulated by dividing the entire length or the number of base pair divided by 10.4 number of base pair. That would be referred to as the standard linking number. So you just divide it out and you would be able to calculate the standard linking number for this DNA molecule. I'm just now do not look towards the video. I'm just turning off the video. You just look towards the theory. Okay, so in theory, what you are getting? In theory, what we get is that, see, imagine a linear DNA in which the two ends becomes connected to form an open circle. There could be a linear double-stranded DNA molecule in which the two ends can lead to the formation of an open circle. This is referred to as relaxed circular DNA molecule. Now, such type of DNA in which the ends are being joined is referred to as circular DNA molecule. Now, there could be another DNA molecule that could be not circular, that could be in a linear manner, that could be present in a linear manner. Now, on the other hand, if the linear DNA was unbounded 10%, that is 50 turns are being unbounded before its ends are joined, then the DNA molecule will be under stress. When the molecule is free in solution, it will coil about itself in space as the two strands simultaneously twist around each other in order to return to the equilibrium value of 10.4 base pair. The DNA is underbound and is referred to as negatively supercoiling. A very, very important line. I'm just going to make you understand this line particularly from the Pathfinder. In yesterday's lecture, I have already shown you all the different animation. Yes, the part of that animation will be shared with you all, so do not worry for that. See, when we are going to talk about the relaxed DNA molecule, now see, such type of DNA which has a standard linking number, such type of DNA was said to be the relaxed DNA molecule. Okay, so that such type of DNA was said to be relaxed DNA molecule. Now the DNA has been made unbounded. That means the DNA is now opened, and then, for example, 50 turns have been opened. Now, what would be the state of the DNA as the DNA is opened? So here, the DNA has become negatively supercoiled. Now, supposing you take the DNA and overwind over itself. अगर डीएनए को लोगे उसके ऊपर उसे ओवरबाइंड कर दोगे तो डीएनए क्या हो जाएगा, then the DNA become positively supercoiled. Okay, so those are the two different types of conformation that could be present in the structure of the DNA molecule. That could be positively supercoiled, it could be negatively supercoiled. Moving forward, now see, this is referred to as linking number. Now see, there is another concept which is given. The helical wind around each other in a right-handed path. DNA is overwound will also relax and assume a supercoiled conformation. Now see, if the DNA is overwounded, if you overwind the DNA molecule, then such type of DNA molecule will also get relaxed themselves, and such type of DNA molecule will also relax and assume another supercoiled conformation. Such type of conformation is said to be the positive supercoiling. Now you have overwounded the DNA molecule. अब जरा इसे वीडियो से समझेंगे प्लीज, वीडियो की तरफ आप फोकस करेंगे, आप मेरे ऊपर फोकस करेंगे, वीडियो के ऊपर फोकस करेंगे ताकि आप वीडियो के थ्रू इसे अंडरस्टैंड कर सकें. Now here is the DNA molecule. I am taking another DNA molecule. Okay, there is one DNA molecule that I have taken here to make you understand how does it appears, what would be the standard linking number. Now I'm taking another DNA molecule, the simplest of the form of DNA molecule. Now supposingly this DNA is right-handedly coiled. Now you coil this DNA in the right-handed direction. Okay, now you are going to coil this DNA in the right-handed direction. Okay, then this is referred to as positive supercoiling. If you coil a right-handed DNA in the left-handed direction, it is called as negative supercoiling. If you coil a left-handed DNA in the left-handed direction, now supposingly this DNA is left-handed, okay, and you're coiling it in the left-handed direction, then what is going to happen? Left-handed DNA coiled in left-handed direction, the answer would be positive supercoiling. Left-handed DNA coiled in right-handed direction, the answer would be negative supercoiling. Okay, now I'm just trying to ask you some of the very important questions. Now see, right-handed DNA coiled in left-handed direction. Tell me the answer. The answer for a right-handed DNA rotated in left-handed direction. Right-handed DNA है, left-handed direction में खोल दिया तो क्या हो जाएगा? Open हो जाएगा. देखो right-handed होगा और right ही handed में आप उसे घुमा रहे होगे तो ये क्या हो जाएगा? पॉजिटिव सुपर कॉइलिंग. और राइट हैंडेड को अपोजिट डायरेक्शन में घुमा दिया तो क्या हो जाएगा? राइट हैंडेड डीएनए को आपने लेफ्ट हैंडेड डायरेक्शन में ओपन कर दिया है तो ये हो जाएगी नेगेटिव सुपर कॉइलिंग. डीएनए रिलैक्स कब है? जब उसका लिंकिंग नंबर एल के नॉट के बराबर है. DNA is said to be relaxed when the linking number of the DNA is equivalent to the LK, not the standard linking number. Okay, now, okay, good, Shreya, you're answering good. Now moving forward, just close the video so that we can focus on the theory part. Now the next part was about the linking number that has already been told to you. What is this linking number? So supercoiling in circular DNA molecule is described mathematically by the number of times the two phosphodiester backbone wrap around one another in a given distance. The quantity is referred to as linking number. Linking number is defined as number of times one strand crosses over the other in a space is referred to as linking number. Okay, so for a bDNA, supposingly 208 base pair is there, what would be the linking number? 208 divided by 10.4. If you divide this number by 10.4, you get the linking number. Okay, so to calculate this particular thing, what do? Calculation of linking number. Linking number equal to total length divided by 10.4. So here is what you would be getting: 208 divided by 10.4. So here you got that number that is referred to as 20. Now this 20 will be referred to as LK naught. I cannot put a naught here, so this would be referred to as the standard linking number. If any linking number is greater than LK naught, hence DNA will be, DNA is positively supercoiled. Okay, ये हो जाएगा positively supercoiling. Hence DNA is positively supercoiled. Just give me a second. This is positively supercoiled because it can come in a single line. It would be better for me to explain it to you all. This is positive supercoiling. Okay, this is positive supercoiling. No, it's not coming in a single line. DNA is positive supercoiling. Nitrogen. Okay, now if you take another example, if LK value for any DNA is less than LK naught, then the DNA is said to be, hence DNA is negatively supercoiled. Negatively supercoiled. Okay, I've explained everything to you through animations also. This is very important concept. That is why I was thinking to explain it to you back. Okay, calculations and questions are being asked from this particular concept in CSIR and other entrance examination, as well as questions have also been asked in IIT-JAM. So it is very important that you can remember these things. Okay, now moving forward, features about the linking number. Linking number is an integer value. Okay, linking number cannot be fractional. I have already told you it is an integer. It cannot be fractional. It is the sum of the two component, the twist and width. I have already told you what is twist. The number of times a DNA is wrapped over itself is twist. The number of times the superhelix of the DNA crosses over itself is referred to as width. The standard linking number has a particular formula, total number of base pair divided by 10.4, that I have just explained it to you, that when total number of base pairs are being calculated, divide by 10.4, you get the formula, and that formula is referred to as the LK naught. Okay, so LK naught can be calculated by using this particular formula. This is the formula that we can use to calculate the LK naught. Now, moving forward, what we are going to visualize here is that there is a specialized component that is given in Pathfinder which has not been discussed in the video. That is referred to as superhelical density. I have already explained what is negative supercoiling, what is positive supercoiling. The two things that I have just explained have also been elaborated here in the theory. The things are, see this, I have just told you LK is less than LK naught, then it is said to be negatively supercoiled. The DNA is much more open, positively supercoiled. When the LK is greater than LK naught, then the DNA is said to be positively supercoiled. I knew that some of the students might have some questions in this particular up till now. If you have any questions, you just put in the chat box. I will answer them up here only, because I want you to understand what is positive and what is negative supercoiling. अगर आपको कोई क्वेरी है तो आप राइट कर सकते हैं, चैट बॉक्स में लिख सकते हैं, मैं तुरंत आंसर आपको दे दूंगा. ठीक है. Now, superhelical density, that is referred to as sigma. It is the quantitative measure of the intensity of the supercoiling. Okay, superhelical density is actually a measure of the intensity of supercoiling, how the supercoiling has taken place. This was not discussed in the previous lecture because this was not included in the animation of Watson and Crick, but it is included in Pathfinder. So this is also a very important topic that is referred to as superhelical density. Now, what is this superhelical density that we will have to visualize? Okay, now moving forward, the superhelical density can be calculated as sigma equals to change in linking number divided by standard linking number. So basically it is represented by sigma. When you take a double stranded DNA molecule, आपने कोई भी double stranded DNA molecule लिया, and after taking a double stranded DNA molecule, what you are doing, you are calculating the change in linking number with respect to the standard linking number. This is the standard linking number, and that standard linking number is LK naught. And this is the change in linking number that is referred to as delta LK. So you would be calculating delta LK divided by LK naught. That means LK minus LK naught divided by LK naught equals to sigma. Now please try to understand this. I would be making you understand through a question. Now see, we can just understand this particular thing via question number 1. Now question number 1 states that if a DNA, if a DNA was having 208 base pairs, 208 base pair in length, and after treatment with an enzyme, it has now a linking number of 18. Case 1, this is case 1, and in another case LK of 25. In case 2, which of the following DNA has what superhelical density? In which case the DNA is positively supercoiled, and where it is negatively supercoiled. Okay, you can calculate it out very simply. Such a simple question. Okay, there is an answer. Okay, the majority of the students are answering. Okay, so see, if there is a 208 base pair of length of the DNA, then 208 divided by 10.4. What we were getting was a number. That one was referred to as, see this, what we were getting. We were getting a number 208 divided by 10.4. We were getting a linking number of 20. When you get a linking number of 20, now see, this DNA has a linking number of 20. Now see, if this is the DNA which is present, it has, sorry, where is the question? Okay, I just forgot to save it. No problem. So if the DNA has a linking number of here 20, should I write? No, I can't bring it back. Sorry for that. Now see, if the linking number of the DNA is 20 and now it has been reduced to 18, then what is going to happen? 18 will come here and 18 minus 20. So the linking number, the superhelical density will be present in the form of a negative value. For a negatively supercoiled DNA, the value of sigma will be negative. For a positively supercoiled DNA, the value of sigma will be positive. So that depends upon the value of sigma that is present there. So it could be negative, it could be positive in nature. Okay. Now the negative sign indicates that the change in linking number is due to underwinding or opening of the DNA. When you see the negative sign, it means that the DNA is getting opened. It is getting negatively supercoiled. This is what is happening with the DNA molecule, that there is a degree of underwinding taking place in the DNA molecule. If you want to ask something, please ask. Do not annotate. I will have to turn off the annotations for you all. Sorry, please do not annotate. That's fine. Okay. Now please look forward. See, if you have any query, you can just write in the text in the chat box or raise your hand. I will answer them. So see, if the sigma has a value of 0.06, that means that percentage of unwinding in the DNA is 6%. That means 6% of the DNA is underwounded. It is open. It is open for everything. Okay. In vitro change in linking number. This indicates that the DNA is actively transcribed at this particular position. If the DNA will have a positive supercoiling, this means that the DNA is overwounded. It is present in a heterochromatin region where the DNA is highly or tightly coiled in nature, so that there is no transcription, there is no translation. Okay, there is a query. Okay. Now see, in vitro change in linking number. Now when we are going to talk about the in vitro change in linking number, that how the in vitro change in linking number occurs, that will have to focus that how these changes occur. The change in the linking number occurs because of the presence of two different enzymes. One is referred to as the type 1 topoisomerase, another one is referred to as the type 2 topoisomerase respectively. So we would be talking about topoisomerases and how does the topoisomerases are going to influence the linking number. In which manner the topoisomerases influences the linking number in the case of double-stranded DNA molecule, changing its conformation from one form to another. I have already told you in my last lecture, that the type 1 topoisomerases were the one that were relaxing the supercoiling. Okay, and the type 1 topoisomerase that relax the supercoiling, and topoisomerase type 2 that introduces the negative supercoiling. Whereas type 1 was relaxing the positive, was introducing positive, relaxing negative supercoiling, and type 2 was introducing negative supercoiling. Okay, so we would be now focusing upon how these topoisomerases functions. What are the function of these topoisomerases and how does this topoisomerase enzyme work? So we will be moving into the active site of topoisomerases, and then talking about topoisomerases, what is their function and how they work. Okay, now see this. We will be moving towards the topoisomerase. This is the first slide.
The topological state of
Just a second. This would be the first slide for topoisomerases. Adjust your volumes accordingly. And now we will be moving towards the slide. I do think that this would be audible to you all. Now just KK sir, you just inform me whether it is audible or not, and let us begin with this.
Of DNA affects its functioning in the cell. Cells use the torsional strain of negative supercoiling to promote strand separation for processes such as DNA replication and RNA transcription.
Cells use negative supercoiling to promote strand separation. Now there are the cells which are there, and cells use a negative supercoiling to promote the strand separation to take place. That how does the strand separation can take place? This can take place with the help of a negative supercoiling, so that the effect of transcription and translation can take place in the case of cells.
However, if DNA becomes too negatively supercoiled, the strands will separate too often, making the DNA more susceptible to degradation.
Now see, if cells in the case of a double-stranded DNA molecule, if the DNA is having too much negative supercoiling, then majority of the strands of the DNA are going to be separated. If majority of the strand of the DNA are going to be separated, the DNA will lose its stability. Please look at the video also. Look at my video. You will be able to visualize it out. I'm just having a double-stranded DNA molecule in front of you. Now, if the strands have a too high negative supercoiling, then the two strands of the DNA is going to be separated apart from each other. When the two strands of the DNA are going to be separated apart from each other, then what you are going to get, this DNA will lose its own stability. As this DNA loses its own stability, so the stability of this DNA is being lost. So that is why too much negatively supercoiled DNA will lose its ability to move or to transcribe and translate, because it will get destroyed, it will get denatured. Okay, now stop the video and let us look at the PowerPoint animation, the animation that I'm showing you. Okay, moving forward.
The topological state of DNA is controlled by a class of enzymes called topoisomerases. Topoisomerases are divided into two broad classes, type 1 topoisomerases and type 2 topoisomerases.
Now, they have been categorized into two different types. One is referred to as type 1 topoisomerase, and another one is said to be the type 2 topoisomerase. Now, how these two differentiate from each other? One utilizes ATP and another do not utilizes ATP molecules. Now, moving forward.
When you have completed this exercise, you should understand how many type 1 topoisomerases can increase the linking number of a DNA molecule by cleaving one strand of the DNA, passing the other strand through the nick, and ligating the nicked strand.
Now see, first you have to understand the mechanism of strand cleavage by type 1 topoisomerase. How does type 1 topoisomerase act? Which is the active amino acid residue that is present in the type 1 topoisomerase, and how it's altered the DNA topology. DNA की टोपोलॉजी को type 1 topoisomerase कैसे alter करता है, इस बात को हमें समझना होगा. Understand how passing the other strand through the nick and ligating the nicked strand changes the linking number. So for that, we would be looking at the structure of the DNA topoisomerase, and then after looking at the structure of the DNA topoisomerase, so after looking at the structure of the type 1 topoisomerase, we are going to look again to what would be the function of this particular topoisomerase. There are some questions. So let me have some questions. Okay, students, the slide is visible or not? You can unmute yourself. Just answer me, the slide is visible or not? Is the slide?
Yes, sir. You can see the people.
Okay, slide is visible. Trishla, you had some problem with your internet. That is why the slide is not visible. else everything is visible. And
So Pathfinder slide is visible, but the video that you playing, that is not visible.
Actually, both cannot come at the same moment, na Trishla? It will come after the next screen share, means video in next screen share only.
Oh, okay.
so it is. So are you able to visualize the video now, or you are visualizing? Okay, 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 okay. I got it out. You must have pointed it out, na? No problem. So now it is visible to you all.
Yes, sir.
Okay, now it is visible to you all. Now we have to what we have.
Yes, sir. At once you can see only one screen.
Okay, okay, no problem. Moving forward. So now see, in this particular, now I will be muting you all. Please mute yourself so that I can continue. We have to understand about the type 1 topoisomerases here, and that how the
Hello,
yes,
hello,
please. Yes, please.
sir. Not visible slides. Slide is not visible properly.
It would be visible to majority of the student. So it is visible to you all or not? All other
Not.
students.
Sir,
Other
Yes, sir.
video
Sir,
screen is
visible.
visible.
video screen is visible. This is what I
Yes.
am talking about. So Rahul,
Okay,
if your screen is
okay, 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 sir. Yes, yes, visible.
Yes, sir, visible.
Yes, sir.
okay. Now I will be moving forward. We have to understand the
Yes,
mechanism.
sir, yes, sir.
Please do mute yourself. Please do mute yourself. Now see, we have to understand the mechanism of strand cleavage by type 1 topoisomerase. Understand how the passage of other strands to the nick and ligating the nicked strand changes the linking number. Now how does this takes place? That we will have to understand. Now see, moving forward, we would be looking at the structure of the type 1
Note,
topoisomerase.
this animation
All these animation are just for structure and understanding. They do not represent the actual
provides an example of the reaction pathway used by many, but not all, type 1 topoisomerases. These type 1 topoisomerases can only bind to segments of DNA in which the two strands are melted, that is, segments where the strands have separated.
Now, steps of cleavage. First, strand of DNA separates. You will have to firstly separate the two strands of the DNA molecule away from each other. Okay, so how this strand separation takes place? This is referred to as the first step, the melting step. Now, how does melting?
One of the DNA strands binds in a cleft in the type 1 topoisomerase.
Now, firstly, type 1 topoisomerase goes and binds to one strand of the DNA molecule. And as it goes and binds to the one strand of the DNA molecule, it breaks the hydrogen bond in between the two strands. For example, now see, there is guanine present here, there is cytosine present here. Now this type 1 topoisomerase goes there and binds to one nitrogenous base, makes a bond with that, and breaks all the present pre-existing bonds which are present. So all the pre-existing bonds will be broken down. I cannot draw certain lines. Okay, so these are the bonds which are already there between the nitrogenous bases. Now this topoisomerase is going to go there and will bind to the DNA molecule and will cleave all these different bonds. Okay, so we are going to move forward and look at the structures. Just clearing the drawing, and we are moving forward.
Placing it near the active site tyrosine.
Now see, the strategy of type 1 topoisomerase is very simple. Okay, strategy type 1 topoisomerase strategy is very simple. When two molecules are being bounded, then type 1 topoisomerase arises, binds with one molecule, and breaks and causes the breakage of all the bonds in between the two molecules. ठीक है, तो देखो सिंपल सी स्ट्रेटजी है टाइप 1 टोपोइसोमरेज की. दो डीएनए के स्ट्रैंड थे, एडेनिन थाइमिन के साथ में बाइंड करा था. अचानक से इन दोनों की लाइफ में कौन आ गया? टाइप 1 topoisomerase. Type 1 topoisomerase came. Type 1 topoisomerase was able to bind with one nitrogenous base. वो थाइमिन के साथ में हाइड्रोजन बॉन्ड कर गया. अब थाइमिन ने जब टाइप 1 टोपोइसोमरेज के साथ में हाइड्रोजन बॉन्ड बना लिया, तो एडेनिन तो ऐसे ही रह गया ना, एडेनिन ऐसे ही खाली रह गया. सो एज type 1 topoisomerase, for example, forms a hydrogen bond, forms an interaction by breaking the phosphodiester linkages which were present in between the adjacent nitrogenous bases through its active tyrosine residue. It will break all these phosphodiester bonds. क्या कहेगा? टाइप 1 टोपोइसोमरेज में क्या है? ऑक्सीजन है. ऑक्सीजन हाईली इलेक्ट्रोनेगेटिव है. ऑक्सीजन इस फॉस्फेट के साथ में बॉन्ड बना लेगी. कैसे देखते हैं.
The active site tyrosine becomes deprotonated.
See, an enzyme is called as topoisomerase because it has an active site tyrosine at 723rd amino acid residue. इस एंजाइम का नाम टोपोआइसोमरेज इसीलिए है क्योंकि क्योंकि इस एंजाइम के अंदर क्या होता है, टायरोसिन होता है. See the name, tyrosine containing enzyme is topoisomerase. Tyrosine position is 723. The question has been asked in JNU. 723 position पे क्या होता है, tyrosine होता है, क्या काम करता है? It helps in breaking the phosphodiester linkages. How? That we have to see. There is a basic amino acid residue. Can you name the 3 basic amino acid residue which are present in a cell, present in the proteins? The 3 basic amino acid residues are arginine, lysine, and histidine. Okay, so supposingly if arginine is present or lysine is present, then it causes deprotonation of the OH group. Now this is oxyanion. Now this will attack the phosphodiester backbone and will break it.
Probably by a nearby basic amino acid residue. The result is a negatively charged oxyanion.
So there is the result is a negatively charged oxyanion. So this oxyanion is negatively charged in. Nothing is audible. If nothing is audible, please to move outside and then move inside. You would be able to again hear it out. Okay. So see, there is a basic amino acid residue which is present. Rahul is raising. Yes, Rahul, do you have a query, a problem? Then you can ask me.
Hello.
Yes, Rahul, any query? Yes, Rahul, any query? You can write in the chat box. There is the chat box, and then you can write in the chat box that what is your query. Okay, I will get it. Now moving forward. Just a second. Now moving forward, because there is a basic amino acid, it will deprotonate the hydroxy group that is present here, and there would be an oxygen negative ion that will be produced. This oxygen negative ion will attack the phosphodiester backbone.
The oxyanion attacks the phosphate group at the 3' position of the nearest deoxyribose, producing a DNA 3' phosphotyrosyl enzyme intermediate and a 5' hydroxyl polynucleotide. The hydrogen atom on the 5' hydroxyl is probably donated by a nearby acidic amino acid residue.
Okay, so while I would be explaining it to you, you can also see what is written here. See how the reaction is going to take place. The oxyanion attacks the phosphate group at the 3' position of the nearest deoxyribose. This is the nearest deoxyribose. The phosphate group has been attacked. The phosphodiester backbone has been broken down. Once the phosphodiester backbone has been broken down, there are intermediates which are being produced. The hydrogen atom on the 3,5' hydroxy group is probably donated by a nearby acidic amino acid. Then an acidic amino acid at the nearby cleft at the active site donates a proton and form 5' hydroxyl group that is being produced. Now this is the 5' hydroxyl group that is being produced.
After cleavage, the enzyme undergoes a large conformational change.
Now see this. The enzyme after cleavage undergoes a large conformational change. Very, very important point. Now see, do you know there were 2 different types of hypotheses for predicting the mechanism of action by the enzymes? Now those 2 different types of hypotheses are, one is given by Koshland and another by Emil Fischer. One was referred to as the lock and key hypothesis, given by Emil Fischer, and the Koshland predicted the induced fit hypothesis. The activity of topoisomerases clearly reflect that induced fit hypothesis is true as compared to the lock and key hypothesis. Activity of topoisomerases indicates that the induced fit hypothesis holds true. Okay, because here there is a conformational change that is taking place within the structure of the topoisomerase, then only the reaction is going to take place and is going to move forward. Okay, so now what we will have to visualize is that how does the reaction takes place. Moving forward, just clearing all the drawings. Okay, and moving forward.
This conformational change opens up a gap in the cleaved strand, with the enzyme bridging the gap.
Now the enzymes will be bridging the gap. How?
The uncut strand then passes through the gap, binding to a pocket in the middle of the enzyme. Binding this strand causes the topoisomerase to change conformation again, closing the gap in the nicked strand.
Now, as the topoisomerase changes its orientation, it passes through the other strand. As it passes through the other strand, it has altered its own conformation. As it has altered its own conformation, so here you can say that the DNA topoisomerase has altered its own conformation and will again join the two DNA molecules together with each other. Please, if you have a query, do write in the chat box. Do write in the chat box. Okay. Now, moving forward,
the topoisomerase then ligates the nicked strand by reversing the cleavage reaction.
Now see, all the cleavage reactions are being reverted back. The hydrogen has been donated by the cleaved 5-phosphate molecule by the 5-hydroxy groups, and then again the proton has been donated to the basically charged amino acid residue from the basically charged amino acid residue, and again the new bonds are being produced. How the new bonds are being produced? Look here.
Finally, the topoisomerase undergoes another conformational change, opening up and releasing the DNA.
Now see this, what is going to happen? The topoisomerase finally moves away, opens up and releases the double-stranded DNA molecule. So ultimately the topoisomerase has moved away.
Overall,
now see, overall how the reaction causes the change in the linking number. Now how does the linking number was being modified in the overall reaction which was taking place, that we will have to visualize.
The reactions catalyzed by the type 1 topoisomerase have added one twist to the DNA, increasing the linking number by 1.
See this, it is going to increase the linking number by 1. In my last lecture, there was some student who was saying, sir, how can we vary the linking number? See, in this particular lecture, I'm telling you, this is how you can vary the linking number. You can modify the linking number by adding the type 1 or type 2 topoisomerase. Now, type 1 topoisomerase, would be other students who might be thinking, sir, this type 1 topoisomerase do not require ATP. Why so? Type 1 topoisomerase को सर ATP की requirement नहीं होती. सर क्यों नहीं होती type 1 topoisomerase को ATP की requirement? For that, you just look at my video. अभी मैं video on कर रहा हूँ. You just look at my video. That is how I will be answering you up. Now, please look at the video of my here. Now, supposingly this DNA is present. Okay. This DNA is tightly coiled over itself. Okay, this DNA is coiled over itself. As this DNA is coiled over itself, okay, this is the double helical model of the DNA molecule that is present. Now, supposingly, if I'm going to chop a strand of the DNA, मैं इसकी एक strand को cut कर देता हूँ blade से. If I'm going to cut a strand of the DNA, if I'm going to chop off a strand of the DNA, which is in the coiled conformation, then what will happen? The DNA will simultaneously relax because it is having a supercoiling present within itself, and that is why to relax over its supercoiling, its negative supercoiling, it will introduce a coiling over itself in the form of a positive supercoil that is referred to as the linking number is going to be increased. Okay, so here we are minimizing the negative supercoiling and moving towards positive supercoiling. Or basically the DNA will move towards positive supercoiling, it will become relaxed. Once the DNA becomes relaxed, it will stop moving over itself. एक बार डीएनए रिलैक्स हो गया तो वो अपने ऊपर और ज्यादा मूव नहीं करेगा. इस डीएनए को अगर आप कट करेंगे तो इसके जो स्ट्रैंड्स हैं वो एक दूसरे के ऊपर मूव करेंगे. जब तक मूव करेंगे जब तक वो रिलैक्स नहीं जाते. लेकिन क्योंकि टोपोआइसोमरेज इसे यहाँ से कट करता है और जैसे ही ये 360 डिग्री पे घूम जाते हैं, इन्हें क्या कर देता है? बाइंड कर देता है. तो नेगेटिव सुपरकॉइलिंग को रिड्यूस कर देता है by 1, रिलैक्स कर देता है by 1, एंड इट मूव्स टुवर्ड्स पॉजिटिव सुपरकॉइलिंग by 1. Okay, that's all. So I'm just turning off the video. So here the linking number is being altered by topological changes within the structure of the DNA. And that topological changes can be done by two different class of enzymes. One is topoisomerase, another one is restriction endonuclease. For example, if restriction endonuclease will degrade this entire DNA, supposingly if restriction endonuclease arise, then what will restriction endonuclease do? Restriction endonuclease will cleave this DNA. See, this is how restriction endonuclease will act. When the DNA will be cleaved, then what about supercoiling? There would be no supercoiling. देखो एक बात याद रखना, टेंशन जब तक ही है जब तक जिंदा हो। अरे मरी गए तो टेंशन काय बात की, ठीक है? You are in a state of supercoiling. You can be relaxed. You can be positively supercoiled. You can be negatively supercoiled. A person who is taking more tension is said to be positively supercoiled. He is taking adequate amount of tension. बहुत ज्यादा टेंशन है एग्जाम का, पढ़ ही नहीं पा रहा है, बहुत टेंशन है। अनदर वन इज कंप्लीटली रिलैक्स, सोए पड़े हैं, जैसे लॉकडाउन में कई स्टूडेंट हमारे सोए पड़े हैं, ठीक है? सो दोज आर द स्टूडेंट्स अंडरगोइंग नेगेटिव सुपरकॉइलिंग। ओके, नाउ if the DNA is being fragmented, if the DNA is being fragmented into pieces, now this DNA is being fragmented into pieces, then there would be no supercoiling that would be left. Then there would be no supercoiling if the DNA is being left into pieces. Okay. Okay, now moving forward, just clearing the drawing. If you have any query, you can use the chat box. Now, so the linking number is being increased because here the twist is also being increased. Now moving forward, listen to the video.
How well did you learn the mechanisms of the reactions catalyzed by type 1 topoisomerases? In this section, you will find out.
This is all about type 1 topoisomerases, how type 1 topoisomerases act. So they are going to increase the linking number by 1.
Question 1. What is the first step of the cleavage reaction? Click on the atoms involved in this step.
Now see, how does the cleavage reaction is going to...
Question 2. What is the second step of the cleavage reaction? Question 1. What is the first step of the cleavage reaction? Click on the atoms involved in this step.
Okay, so in the case of first cleavage reaction, what you are going to do is you are going to deprotonate this proton. Rahul, I am trying to unmute it. You are not answering to me. You are again and again raising your hand. Please ask your query. If you have a query, you ask your query, Rahul. You didn't have a query. Then, okay.
Incorrect. You may want to try again.
I'm just pressing all these things. That is why this is happening. Now, moving forward. What is this happening? There. No, this is what is going to happen. Now see, this is how this nitrogen is going to act, and nitrogen is going to deprotonate this particular oxygen molecule, and then this oxygen molecule will attack the phosphodiester linkages. The phosphodiester bonds will be broken down, and again there would be another ester linkage formed between the oxygen and the phosphate molecule that will rotate around the DNA molecule and will ligate the DNA molecule. So this animation finishes here about the type 1 topoisomerases. Now we have to look towards another topoisomerases that is called as the type 2 topoisomerases. So firstly, going towards Pathfinder, what is given there in the case of Pathfinder that we will be looking forward. Now when you're looking at the Pathfinder, then see, we were talking about the type 1 topoisomerases, type 2 topoisomerases. Not more information is being given here. Here it is only written about the type 1 and the type 2 topoisomerases. So moving forward towards the type 2 topoisomerases, in the type 1 topoisomerases, you have seen that these type 1 topoisomerases were inducing the positive supercoiling and were reducing the negative supercoiling. The opposite will be true for the type 2 topoisomerases. Type 2 topoisomerases will induce negative supercoiling by a fraction of 2 or will reduce the positive supercoiling by 2. Okay. Okay. Uh, Please ask Rahul. Please do write it down, or you just speak it so that I can answer you. Okay. Now, moving forward, when we are moving forward, we have to look towards the animation of the type second topoisomerases. How does type second topoisomerases work? That we have to see. Now, we will be looking at the activity of the type second topoisomerases. Just a second. This is type 1 topoisomerases. Okay, that is the only animation that we are having. Okay, no problem. We'll be looking at the activity of type second topoisomerases from STRIR, where yes. So what I am saying to you, Namrata, that yes, topoisomerase 1 is also relaxing the supercoiling, but which type of supercoiling it is relaxing? It is relaxing the negative supercoiling here and is introducing the positive one. Yes, we have studied right now that type 1 induces supercoiling. No, it actually causes the induction of positive supercoiling, reduces the negative supercoiling by a fraction of 1. So it is the one that will be inducing towards positive supercoiling or decreasing the negative supercoiling. There was a query from one of our students. Now moving forward, we would be now switching ourselves to the Pathfinder again. Now we have to look towards the structure of ETBR. There is a compound that we are going to talk about. One that is referred to as ETBR, Ethereum bromide. Now, how does this Ethereum bromide act? This is a chemical agent which is highly carcinogenic in nature. Now, the function of ETBR and how does this ETBR act? ETBR is present in the beef. ETBR is a planar molecule. This is a planar molecule. This is ETBR, a planar molecule. This planar molecule can move between the strands of the DNA molecule. It can move between the strand of the DNA molecule and act like a jack. As there is a jack to increase your car height, so ETBR works. ETBR moves in between the DNA strands and then stretches itself in such a manner so that it increases the distances in between the two strands of the DNA, two nitrogenous bases. It increases the distance between the two nitrogenous bases. This is how ETBR function. ETBR मूव कर जाता है, प्लेनर स्ट्रक्चर है, एक प्लेन एक पेज की तरह है, तो आराम से दो स्ट्रैंड के बीच में दो नाइट्रोजनस बेसिस जो होते हैं एक स्ट्रैंड के बीच में उनके अंदर चला जाता है, उनके बीच में चला जाता है, और बीच में जाने के बाद में उनके बीच में डिस्टेंसेस को क्या कर देता है, बढ़ा देता है, जिसकी वजह से वो स्ट्रैंड्स के इलेक्ट्रोनेगेटिव क्लाउड अब इंटरैक्ट नहीं कर पा रहे हैं. तो अब जो इलेक्ट्रॉनिक क्लाउड्स हैं वो आपस में इंटरैक्ट नहीं कर पा रहे हैं. क्योंकि इलेक्ट्रॉनिक क्लाउड्स आपस में इंटरैक्ट नहीं कर पा रहे हैं तो यहां पर यूवी रेडिएशन का एब्जॉर्बेंस बढ़ जाता है. अब आप इसमें वीडियो से समझें. मैं अपने वीडियो को ऑन कर रहा हूं. यू कैन लुक एट मी इन माय वीडियो. You can see that there is a DNA molecule that I have brought for you all. So this is a gift for you. Now see this. Okay, I'm not giving it to you. So see, this is a double-stranded DNA molecule. Supposingly, if this is adequately visible to you all. This is a double-stranded DNA molecule. Let me take this double-stranded DNA molecule. It is visible to you all. Now see, there are nitrogenous bases that would be present. Now, what is going to happen? ETBR is going to move in between the two nitrogenous bases and then is going to push the two nitrogenous bases. देखिए, this is how ETBR acts. So ETBR कैसे फंक्शन करता है जरा समझने की कोशिश करें. आप कभी EMU पैसेंजर में गए हैं? Have you ever went to Delhi in an EMU passenger? Majority of you would have went. See, EMU passenger is a train in which everyone is there.
Hello. Hello.
Yes. Yes,
please sir. Slides is not visible.
See, if the slide is not visible, just move out and then again log in because your internet connection is unstable. Else the slide would be visible to all. Okay.
Okay, sir. Please, ये जो slides
that would be made visible to you all after this particular class. That is why please, I'm reading all your messages. That would be made visible to you all in the group. Also, it has been made visible because they have been shared. Probably you have joined the group late. That is why you are not getting my point. So please wait for the lecture to be over. I will Now, I will inform you about, I will deal with all your queries, okay? Because the lecture is also being recorded for you all,
Okay, okay,
okay?
okay, okay, sir. Okay.
Thank you. Now, moving forward, now see, when you would, for example, if you are talking about the ETBR, what is the function of ETBR? How does ETBR act? Now, ETBR function could be understood by looking at the setting arrangement in a normal train, in the local compartment of the train, जर्नल के डिब्बे में, ठीक है? क्या होता है, एक सीट है जिसपे 4 लोग बैठ सकते हैं, 5 लोग ऑलरेडी बैठे हुए हैं। एक अंकल आंटी आते हैं जो बोलते हैं बेटा थोड़ा सा इधर खिसकना, बेटा थोड़ा सा इधर खिसकना, आपको इधर उधर खिसका के बैठ जाते हो और आखिरी में थोड़ी देर में हम देखते हैं किनारे वाले बंदे को गिरा ही देते हैं सीट से, वो बेचारा गिर ही जाता है, ठीक है? दिस इज व्हाट हैपेंस इन द केस ऑफ अ लोकल कंपार्टमेंट ऑफ अ ट्रेन, okay? So here is how ETBR functions. ETBR moves in between the two nitrogenous bases of the one strand of DNA. The single strand of DNA containing n number of nitrogenous bases. ETBR moves in between them. As ETBR moves in between them, it separates the two strands of the DNA by increasing its size. ETBR खुद डीएनए के दो नाइट्रोजनस बेसिस के बीच में घुस जाता है और खुद इंटरेक्ट करने लग जाता है उन नाइट्रोजनस बेसिस से। तो ये क्या कर देता है, डीएनए को क्या कर देता है, इट अनस्टेबलाइजेस द डीएनए मॉलिक्यूल। देयर वाज वन नाइट्रोजनस बेस, देयर वाज अनदर नाइट्रोजनस बेस, both these nitrogenous base electronic clouds were interacting with each other. When both the nitrogenous base electronic clouds were interacting with each other, ETBR seeps in between the two electronic clouds. As ETBR moves in between the two electronic clouds of the two nitrogenous bases, it causes the minimization of interaction in between the two nitrogenous bases, breaks the hydrophobic base stacking interaction. The most important function of ETBR is to break the hydrophobic base stacking interaction. It moves in between the two nucleotides of a strand of DNA and breaks the hydrophobic base stacking interaction, okay? So this is stacking interactions is being broken down. As there is no hydrophobic base stacking interaction that is going to take place, then what is going to happen, the DNA will lose its stability and will absorb more UV radiation, thus making the DNA free for absorbing more UV radiation, okay? This is how DNA is going to absorb more UV radiation. Another thing that is being requested to you all students, see why I'm teaching through Pathfinder is to provide you all the notes that are already included in Pathfinder. This would remain the standard book for our teaching throughout the session of 7 months in which we would be talking to you. See, in tomorrow lecture, I would be discussing about the MCQs, the multiple choice questions that have been asked from the topic of nucleic acid up till the point or up till the topic, up till the fraction of this chapter that will be completed in today's class, so that you can have an idea that this type of questions are being asked in CSIR, in IIT-JAM, and in other entrance examinations. And we would be solving all those different questions. The MCQ book is available with majority of you, and if it is not available, I have also uploaded that book in the group so that you can visualize that book, that what is being given in that particular book and which questions have to be answered. No, Shreya, just wait for a second so that I can clear this out. Now see, ETBR is a fluorescent dye generally used to stain the DNA molecule for its visualization. So ETBR is being used for its visualization. So this is the one that we use for the DNA visualization to occur. So this is how the ETBR can be effectively used for the visualization to take place. Okay. It can be effectively used for visualization. ETBR decreases the number of turns needed to create an unconstrained duplex. It decreases twist. The twist is being decreased since linking number does not changes when without the molecule is being broken. The breadth component is also being affected. So breadth is also being affected. It decreases the twist. in the case of a double-stranded DNA. Okay, the number of twists devoted to width increases. In other words, ETBR increase the positive supercoiling of the molecule. This question has also been asked. ETBR causes the molecule to become positively supercoiled. ETBR क्या करता है? ETBR DNA को positively supercoil कर देता है, उसके अंदर supercoiling को क्या कर देता है? Induce कर देता है. Does an underbound molecule tend to become relaxed? अब देखिए, अगर एक अंडरबाउंड मॉलिक्यूल है, यानी कि देखो नम्रता, तुम्हारे क्वेश्चन का आंसर, इफ देयर इज एन अंडरबाउंड मॉलिक्यूल, ओके, इफ देयर इज एन अंडरबाउंड मॉलिक्यूल, व्हाट डज दिस मीन? What does this mean? This means the molecule is negatively supercoiled, and you add ETBR into it, it becomes relaxed. Why? Because it is minimizing negatively supercoiling, it is making the molecule to move towards positive supercoiling. But the DNA will stop its movement once it gets relaxed, because it loses negatively supercoiling. Okay, whereas the relaxed closed DNA duplex becomes overbounded. When you take a relaxed DNA molecule, now supposingly you take a relaxed DNA molecule, then ETBR is going to, what would be the function of ETBR now? Now the ETBR will cause the relaxed molecule to be overbounded. That means it will cause positive supercoiling to be introduced. Okay. There is a question from one of our students, sir, ETBR जब negative supercoiling DNA से bind करेगा तो क्या होगा? तो DNA को relax कर देगा. See what is happening in the case of a negatively supercoiled DNA molecule. If ETBR binds to a negatively supercoiled DNA molecule, it will lose its negative supercoiling and the DNA will get relaxed. ETBR increase the positive supercoiling, thus an underbound molecule. Underbound molecule का मतलब क्या है? Underbound का मतलब क्या होता है? Negatively supercoiled molecule will become relaxed in the case of ETBR. In the case of a relaxed molecule, it will introduce positive supercoiling. Okay, so this is how ETBR is going to function. So what is the function of ETBR? The function of ETBR is equivalent to the function of DNA polymerase 1. Is equivalent to the function of DNA topoisomerase 1. Topoisomerase 1 was also increasing the positive supercoiling. ETBR is also increasing the positive supercoiling. So Shreya, it is very clear to you and to other students that ETBR increases the positive supercoiling. Any other student, any query, you just write in the chat box. I will answer it to everyone. Please explain function of ETBR. I have already told you ETBR increases the visualization efficiency of the DNA under the UV light. DNA can be effectively visualized under the UV light because it increases the absorption of the UV light in the DNA molecule, as it separates the two nitrogenous bases apart from each other by breaking hydrophobic base stacking interaction. Okay. एक और चीज पूछी गई है, ETBR कितने डिग्री से रोटेट कर देता है डीएनए को? इट रोटेट इट बाय 27 डिग्री. ओके, see, I have to move fast because I have to cover the syllabus also, else it won't be covered. You can just go through the recorded version of this lecture and again visualize it up. Okay, now DNA as genetic material. Now, when we are talking about the DNA as a genetic material in nature, then there are several different types of experiments which have proved that DNA exists as a genetic material. Before DNA, there was a concept of RNA world hypothesis. According to the concept of RNA world hypothesis, it was predicted that before DNA, the entire world was being constituted by certain was being predominated by certain RNA molecule, and that hypothesis is referred to as the RNA world hypothesis. Here you can find the RNA world hypothesis. This hypothesis is based on the RNA ability to act not only as a genetic material but also to act as a ribozyme or as a ribosome. So RNA could act as a genetic material. It could also be used in the form of ribozyme. It could also act as a ribosome. However, once protein which can form enzyme came into action, then there was no need of such type of a genetic material. फिर इस genetic material की नीड क्या हो गई? खत्म हो गई. जिसके बाद में हमने क्या किया? Then it was being followed by the next genetic material, and that one was referred to as the DNA. as proteins were being formed, so there was a need for more stable genetic material to be developed, and second genetic material which was being developed was DNA. So after RNA, the second genetic material was being developed, and that one was referred to as the RNA, the DNA molecule. After RNA, the DNA molecule developed. Okay. Now, the first experiment that was being conducted in order to explain the genetic inheritance of the DNA was the Griffith experiment. In the case of Griffith experiment, what was being done? You would have already studied this Griffith experiment, but now in today's lecture, we will be talking about the Griffith experiment in a completely different manner. There were two different strains which were being taken. One was referred to as the R second strain. Another one was referred to as the S third strain of an organism that was referred to as pneumococcus, also referred to as the diplococcus. So diplococcus and pneumococcus strains were being taken for diplococcus pneumoniae or streptococcus pneumoniae in class 12th.
Hello, hello, please listen me. Hello, sir. Hello.
Yes, Peter. Rahul, I can listen you, but sir has muted his speaker, I think. So let him unmute himself.